Hello, how y'all doing today? My name is Bernie Thompson, and today we're going to take a look at a 2012 GMC Terrain. This Terrain has a 2.4 liter engine in it, and apparently we're setting lean conditions for the engine. So the first thing that we need to do is we need to put the escan in this vehicle so I can collect some data. Once I've got the data, then we can make some diagnostic decisions on what to test. So let's go ahead and get the escan connected to the vehicle. The first thing we're going to do is we're going to mess with this customer's discount. We're going to disconnect the insurance connector, and we're going to put in the escan in its place so we can gather data. Now the escan is communicating with this GMC Terrain, we can get the DTCs. We know there's DTC set because we have a check engine lamp. That being said, we want to go read these. So let's go to DTCs and open them up. We have a P0133, the O2 sensor response is slow. We have a P2229, barometric pressure circuit is high. We have a P0171, the system is too lean, bank 1. Now that's the code why I'm here. The shop has been trying to fix this too lean code and they haven't had very much success. Now we just need to diagnose it so we can get the car fixed. While we're here, I want to go to mode 6. Open up the window and come down, and you've got to always pick the type of car that you're working on. In this case, we have a GM, so we're going to pick GM, and then we're going to read the data so we can see if anything has failed in the mode 6 data. Here we do have something. Our rich to lean switch time has broken its threshold. The lean to rich switch time has broken its threshold, and we have a delayed response from the O2. All have failed the last test that was run. Mode 6 basically gives you an indication of the last test that was run and if it passed or failed. We want to go down and we want to look at the rest of this data. Now these misfires haven't failed the cycles, but I can see where I have misfires, and the misfires are on all the cylinders. So that's sort of an interesting thing. Maybe it really is too lean and we've got some missing cylinders from the lean coating. What we really need to do now is we need to go test drive this car and run specific tests on this vehicle so we can diagnose it rapidly. So let's go drive this vehicle. Now is what we want to do is we want to come over to the sharpshooter where all the action's going to happen. I want to pick long plus short term. This is total trim. We want to start the test, and now that we've got the test running, we want to drive the car. So as we drive the car, all we're going to do is we're going to accelerate the car through this gear, and then we're going to collect this data. So we've made one pull with this data. Let's just stop and take a look at the pull. Wow, we have some pretty big trim numbers here. So we have 60s and 70s on the trim. Guys, I don't know about you, but you rarely will see 60s and 70s on trim. Most of the manufacturers are afraid to give too much fuel or hydro the motor from problems. So this is a lot of trim. Most cars won't give you this kind of trim counts. So we have a severe problem. So now is what I want to do is, since the fuel trim is always about the air, we need to run an air equation. We're going to go to the VE and we're going to start the VE. I don't want to record the data, but we do need to check the data. We have a 2.4, it's about 80 degrees, so that's very close, and my elevation is correct. So we're going to go ahead and tell it to run the test. And notice this right here where it says scaled engine. This right here is telling me that we have models of this engine, so this should be a pretty accurate test on this one. When it says generic, it may or may not be correct. So now we're going to do a pull. Okay, so we want to go ahead and stop the data from being collected. We did the pull. The yellow trace is the actual mass airflow gram weight. The red trace is a theoretic model. This is actually an engine model that we build at ATS. Now you can see how all of these are green. That means they're good, and we can see that we're 1, 3, zeros, really close, and we can also see that these two traces laying on top of each other are really close. When we look at the fuel trim, these are huge numbers. So this problem is not being caused by an error problem. We're going to go ahead and take the VE and this is the VE and the fuel trim compare. We're going to load this and we're going to compare them. Now, if it was an air problem, this air would lay right on top of the fuel trim. But we can see that this is not the case. They're way apart from each other because the air equation read right and the fuel trim, look at this, 50%, 70%, and it went to 70% and stayed there through that pull. I've hardly ever seen that much fuel trim on a vehicle. So this is a pretty cool car. I like this car. So what this tells me right now is that the air is being read correctly, but we have a great fuel trim problem. So we want to go and we want to take a couple other looks right here. One of them is on the power. I want to see what kind of power we made. So what we see is that we have an engine that can make 82 horsepower, but the actual and the theoretical are coming up very close. So the fuel trim, whatever it's doing, it thinks it's making the right amount of power. The car runs okay. At idle, it almost feels like it's a little rough, but pulling, it felt like it pulled okay when I got in it. The next thing I want to do is I want to run a CAT efficiency test. Now this CAT efficiency test, we would normally populate all these, but we just want to get this done for the video. So we're going to go ahead and start this. Now with those kind of trim numbers, you cannot count on anything being accurate, but I want to just see what the CAT says it's going to do. The CAT could have a problem with 70% trim adds. So what we want to do is we're going to just take a quick look. Always remember that this data is not going to be very accurate for us. And we can basically see that we have very little oxygen sensor movement here. That oxygen sensor on the front isn't moving. And we can see that it's failing our testing procedure. But that doesn't mean that the CAT's bad, guys. All that means is we need to go fix the problem and then make sure that the CAT's okay on this car before we release it. So let's go back to the shop and do some tests. We're going to need to hook up an oscilloscope to the oxygen sensor to see what's going on with that sensor, because we definitely don't have very much transitional movement. So let's go back to the shop now. Okay, so what we want to do now is we want to take the oscilloscope and we want to hook the oscilloscope into the oxygen sensor. Since we don't really know what's going on, the scan tool is only an interpreter. It doesn't tell me what's really happening on the wires. So what I want to do is I want to get into the oxygen sensor and I want to get into the battery ground. So basically we want to go ahead and connect the scope up. First, we want to get into the battery ground. Oh, wow. Okay, guys, I want you to look at this. Do you see how corroded this battery is? Now, that's a bad problem because I can't see a voltage drop. If I get on the outside of the post and it's got a lot of corrosion between the battery and the post, you can't see the voltage drop, and that could give me a problem. So we don't want to take it apart. If you ever see this, don't take it apart to clean it now. We will need to take it apart and clean it once we're done with the car. Right now, I don't want to change anything. I don't want to disconnect anything until I know what I'm disconnecting. So the game I'm going to play is I'm going to take a screw and I'm going to put a screw right down into the center of that battery post and I'm going to connect to it. Now any voltage drop that I have between that connector and the post of the battery, I'll see that. So let's go ahead and get this connected. Okay, so when you put the screw in, never put it in between the clamp where it could catch the clamp and that post. When this screw goes in, it needs to go directly into the center of the post. This screw, if you put it on the edges, it could screw into the post and this clamp, and it can hide your problem, and then you take the screw out and you have the problem back. When we're looking for voltage drops, we always want to be at the battery negative. To make sure we have a good connection, we're going to put this right into the center of this post. So there we go, we've got the screw in now. Now that we got the screw directly into the battery post, we're going to go ahead and connect to the screw. That gives us a good ground plane with the oscilloscope. We're going to now take channel 1 and channel 2, and we're going to get into the front O2 sensors, output, and the redundant ground. Let's go ahead and look at those signals now. Now that we've got the oscilloscope connected, we've got it on a digital meter reading. We have 0.8, which you guys might think is rich, like it's a high voltage output from the O2 sensor. But that's not right on this car. Do you see how the redundant ground has 0.69? This should have 1 volt on it. Now if you've got a Volvo, they put a bias voltage on their O2s of about 0.7. But I'm pretty sure on this GM, this should be 1 volt. That means that this is already low by 0.3 of a volt. Now if you only make 0.09 of a volt or a volt, 0.3 of a volt is over 1/3 of your voltage. So that's going to make the computer think that this system is lean. So something's wrong here, but what's really got me is the bias voltage. It should be higher. Now what I want to do is I want to see if this can get higher than this. So what we want to do is we want to go over and we want to bring up this, and we're going to set the scope up a little bit differently. I want more time. So now we have 20 seconds of time, and we're recording those 2 traces. So let's give them a couple of hits with the throttle. Now that should have made that O2 sensor go high. And we can clearly see the O2 just isn't working correctly. So this O2 has some type of a problem, but the most important thing is, why is my bias voltage low? Because this should be higher. So this O2 sensor definitely isn't working correctly. Anytime I have a low voltage state on a sensor like an oxygen sensor or a TPS or an APPS or some type of sensor that doesn't generate very much current, the first thing that I'm always interested in is anyone pulling that current down? In other words, if the O2 has a problem or the computer has a problem, it'll pull that voltage down because there's no current in the circuit. There's only a potential change with very little current. So if anything has a path where that current can be drained off, it would pull these down. But the bias really isn't producing voltage, the O2 is just riding on it. So we sort of have a problem with the O2 where it doesn't seem to produce, but what it's riding on is 0.3 of a volt low. So that's a problem. So what I want to do, I don't want to disconnect anything till we test it. I want to take and I want to put in a voltage output from the scope, and it is a 0 to 5 volt signal, and then we're going to see if it'll pull that signal down. If that signal gets pulled down, then something in this circuit is pulling it down, and we can put all the parts on you want, and you're not going to fix it until we figure out what's pulling the circuit down. So let's go ahead and do that. In order to run this test, the engine and the key needs to be off, so we're going to kill it. Now we're going to go up front again. The escope Elite has two outputs. One sinks power and one sends voltage out. The TTL out sends a 0 to 5 volt signal out of it. So that's what I want to get in. We're going to get in this signal right here, and now I'm going to send voltage into the circuit so I can see if that circuit is being loaded or not. Now that we've got the TTL output lead connected, we need to set up the scope so we can have an output on this lead. In order to do that, I want to come to outputs. Now right here where it says the frequency is on for 1 second, that means it's going to turn on for 1 second and then it's going to turn off. So I don't want to do that. What we want to do is we want to come in and put a 0 in that window, and that means it's going to run indefinitely. So now it's going to run indefinitely at 25 hertz at a 50% duty cycle. We're going to start that, and now we're going to send the signal out. In order to test this signal, first thing we want to make sure that it's being sent out. I want to take the green lead and I want to connect it. Now you can see where I'm making that frequency. Now that frequency it's important to realize that's going to 5 volts. So when I connect this to the O2 signal, I should have 5 volts. If the O2 bulb is cold, the O2 has greater than 100 million ohms. It's an open. The other end of this circuit goes either into a MUX, a multiplexer, or it goes into an ADC, an analog to digital converter. Either of those have greater than 1 million ohms. So if I connected into this wire, I wouldn't expect very much voltage drop. When I connect this into this type of a signal for the O2, I should have really close to 5 volts that is present. Again, if I connect that, I can see the voltage. And when I disconnect it, I don't. That's 5 volts amplitude. So now is what we want to do is let's go ahead and connect this to the circuit and watch the scope. So what we need to do now is we want to connect the TTL output into this lead back here. Once I'm touching it, and I know I'm touching it, now we're going to check the scope and we're going to see what the amplitude of the TTL pulse is. Okay, so now we're going to touch the output from the O2 sensor, and you can see that we have the signal being injected into the circuit there. Now what we want to do is we want to come out here and we want to stop this. We want to get the zoom window and we want to come in, and what I'm interested in doing here is I want to measure this. So as we can see, we only got 3.2 volts on that. We don't have 5 volts, guys. So without having 5 volts, that circuit is loading. And if it's loading this circuit, it's going to load the O2 sensor circuit. So the O2 can't put out. So the O2 is being loaded, and there's also some problem with the bias voltage, because I'm still pretty sure most of these GMs I've checked, they're at 1 volt. So we have 2 problems. One, the O2 is being loaded by the circuit, and we have some kind of a problem with the bias voltage. Now we need to test this, so the way we're going to do this is I'm going to release the connector on the O2 sensor, and we're going to release it while we're in the harness. Now if we're in the harness side and it pops up, the O2 is the one that's loading it. If it still stays loaded, what we've got to do is we've got to unplug the computer. If we unplug the computer and it pops up, the computer is the problem. If it still stays down low, it's in the wiring harness. So by just putting the signal into the wires and releasing each end one at a time while we're watching the scope, we can come out with the idea of where our problem is very quickly, very accurately. Now before I release anything, I want to show you guys one other test that you need to know about. If you have a problem with fuel control, one of the easiest things that you can do is to use a 5-gas analyzer on it. You put a 5-gas in the tailpipe and you look at the lambda. If the lambda is 1 or stoichiometric, that means that the fuel control system is functioning. If you've got an O2 that's moving around up and down like this car, and I'm adding a lot of trim, it should be at stoke if it's reading right. If something's wrong with that O2 circuit, the feedback circuit, it can't be stoked anymore. So what that means is if I have a gas analyzer, all of these fuel control problems become really easy. So what we want to do is take a gas analyzer, put it in the tailpipe, and if the fuel control system's movement or the fuel trim was correct, I'll have stoke, I'll have a lambda of 1. If it's incorrect, then that shows me that I have some type of a problem in the feedback system. So before we unplug anything, let's do one more test. So let's get the 5 gas. Now that we've got a 5 gas analyzer connected to this Terrain, what I'm interested in looking at is the gas basis. When we look at this, we have a lot of 8C. The CO is way high, CO2 is way low. The oxygen is about right. But the oxygen is right because I am way rich. 0.76, that's 24% too rich. This should be 1.0. That would be a lambda of 1, which means that I'm stoichiometric. Now this is not stoke, this is way rich. The O2 system is used in this car as a feedback circuit. Well, if the O2 can't produce enough voltage, high voltage, the feedback saying, I'm lean, I'm lean, I'm lean, and it wants to keep adding and adding and adding trim to try to get the O2 up. But the O2 can't come up because something's wrong with the circuit. We've already tested the circuit and we see the circuit is being loaded. So if I'm loading the circuit, the O2 sensor can't produce a high voltage because the system is pulling that voltage low. And this indicates that the gas base is incorrect. So you guys that got gas analyzers, get them out and use them for diagnostics. This tool wasn't made as an emissions tool. This tool is made as a diagnostic tool. It was made in the 50s. Back in the 50s, no one was worried about tailpipe exhaust. They were worried about how you fix cars. And a 5 gas is a great way to test the feedback circuit. If I've got 30–40% trim and I've got a lambda of 1, the trim corrected the problem and it did the right thing. If I'm adding 20–30% trim and the lambda is way too rich or way too lean, the feedback controls something's wrong with either the RAF sensor, the O2 sensor, but you got something wrong with the feedback. In this car, we already know that that feedback circuit is being loaded. Now that I've showed you how to use your gas analyzer, let me show you how we're going to find out which component is loading the circuit. Okay, now we need to test the circuit for the O2. So what I did is I came and I found the wiring diagram and I found the wires. The purple white is the signal wire and the tan white is the redundant ground. This is the one that has the bias voltage on it. Now this goes into the ECU. What I want to do is I'm going to take the TTL out and I'm going to plug it directly into the signal out. Now is what I want to do is I want to come over and we want to start our output up. So it was already going. Let's start it up again. Now we can see this. Now what I'm going to do is I'm going to unplug the O2 sensor and we're going to watch that signal. So let's unplug the O2. The O2 sensor has now been disconnected, but I don't see any change in the frequency that I'm sending into the signal, so it's still being pulled down. So now is what I need to do is to disconnect the connector off of the computer so the computer is free from that circuit. Let's go ahead and do that. Here's where the connector to the ECU was connected. This is where I disconnected it. I want to note one thing. Do you see how the redundant ground, which carries the bias voltage fell open because it's not connected. These wires aren't connected to each other. When this one came up, because we're feeding the frequency into this one and this fell, that means that there's no loading between these two circuits. So what this is indicative of is these two circuits are free of each other, so that's good because that could also load the circuit. What's happening is something's wrong with the ECM, and there's something on the board, or maybe an electrolytic capacitor leaks some acid and it's got a path. There's many different ways that a capacitor could fail and possibly pull a circuit down like this. Through the filtering circuit, there's high and low pass filters on these, but something is pulling on that circuit, and you can clearly see when I put the signal in and I disconnect it. First we disconnected the O2 sensor. There was no change. That means it's not loading. Then I disconnected the ECU circuit and it popped up. If it would have stayed down, pulled down, that means the problem is in the harness. Now we know the problem is in the ECM. This ECM is going to need to be replaced. Now before you replace any module, you always have to go through all the powers and all the grounds and the 5-volt references. Go through each one, voltage drop them, and make sure that they're okay. Once those are okay, we're set. Then you replace the module and this car will be back running again for your customer. And I don't know if they're going to replace this ECM or not. This is the shop's, they got to make their decisions. I'm just here to diagnose the car. But what I really want you to understand is by using sensor simulators, you have a huge gain in your diagnostic strategies, because I can test something and I can test for a circuit being loaded without ever disconnecting anything. As soon as you disconnect things, things can change. So whenever you disconnect something, make sure that you know why you're disconnecting it and what you're expecting the outcome to do. Many shops I go to, they just start disconnecting connectors, and then that sets up defaults within the system and they get confused. Don't be confused. Stay on target. The ATS equipment will help you stay on target. Hey, good troubleshooting in your base.